Okay, guys, I'm going to go ahead and start. And I apologize, it's going to be a little hectic tonight. I want to only go about an hour just to sort of get everybody's juices flowing. Candy bucket's here, so just keep passing it around until there's none left. I'm going to call the roll real quick just so I can sort of get a name with a face. Alex, you want to introduce yourself real quick? Alex is going to be your TA. He sits about 3 feet from me 90% of the time, so when you see him, you're basically seeing me or a better looking version of me. So Alex's information is on the info sheet up here. I know it's a little bit hard to read. Looks like we already have one bug. I listed myself as a TA. Sorry about that, Alex. Um, there's going to be lots of bugs. Okay, so I know I make lots of mistakes. So go ahead, tell them a little about yourself and. Okay. Okay. Thank you. You may be wondering why I wear headphones, and it's because I'm making a backup recording. We've had historically, if there's going to be a problem with the ecosystem, it's going to be at night, and we meet at night. So last time in the summer, we probably had, 3 out of 7 failures or something. And so making a backup video protects me, protects you, keeps us all happy. We don't want to do this again. So I know I look kind of like an idiot. I tried some USB headphones and they were okay, but they picked up a lot of background noise. So this is sort of the best thing to do. And yes, I know I have a limited, leash here. So if I get really excited, then, I'll pull it out and bad things will happen. The video will stop and everything else. But okay, really quick, I'm going to call everyone's name just again so I can get a name with a face. First one off the bat is a doozy. Agrazyeva. Ah, that's a good one. We're just going to call you Zinyatt. Okay, very good. I like that. Mr. Bauer. Okay, good. Mr. Burkhart's here. Mr. Chaudhary. Okay. Mr. Chingal Prasan. Where is he? Yep. Mr. Dean. Mr. Dean, not here today. Not making a good impression. Jaffer, not here. Okay. Mr. Duca, guess you're here. Very good. Mr. Frick, I assume Mr. Yep. Mr. Fulford is not here, right? He's online. Ah, look at this. Came up for this. Great. Okay. Mr. Fulford is going to be one of those who drives up here every class period. I hope not every class period, but he probably will. Yeah. Mr. Guo, X-I-N-Y, Zingy. Ah, okay. My apologies. Sorry. Not so good with Mr. Hernandez, Joshua Joel. Okay. Miss Hugh. She's there. Okay, very good. Sorry? Yeah, that's you. And Mr. Quo is en route. He had a travel thing, E. Mr. Lonsall. Olivier? Ah, don't worry. Mr. Limon? Yeah. Hanyu, Donde? Okay. There's 3 Lius. Okay. This is going to be good. Ching Liu? Okay, very good. What do I call you instead? Hyson, okay. How about I call you Lou number 1? I don't Sherry Liu. Okay, very good. That's easy. Tian Liu? Okay. Don't, please don't sit together. Oh my God. Okay, Ruben's here. Mr. Richardson. Okay, very good. Abhishek. Okay, very good. Mr. Sivan. Yep, nice. Mr. Syed. Okay, very good. Uh, I assume this is a Mr., but it might be a Miss Yang. Uh, sorry? And you just want to be called she or? Okay. And did I miss anybody? Okay. Yep. We put you down as a question mark. Now we'll put you down as a check. Mr. Churchwell is online, and I will try to get some more people to take this online, so hopefully he will. There's a lot of you, and I think you're really going to enjoy this. I know every time somebody starts a class, they always say how much fun it's going to be. You have 27 lectures that are going to change your life. Each one is going to be different in some way, shape, or form. We're going to try to present the material in the most effective way we can, but obviously you've got to do a lot of reading. There's something going to be called a base lecture folder. All of these are on the server. And the base lecture folder has all the historical information. And then I've made a secondary lecture which I'll present, and that file will generally be placed in the folder before class, sometimes like right before class, like today. What I try to do is make really high resolution files, and so it takes some doing. And Alex probably heard me cursing from my office today because sometimes things don't work in high res. I know this is really small. Someday we'll get a bigger screen. My apologies. Feels kind of like 1950s, everybody sitting around a small television set. But just to make this easy on you, I'm sure everybody's figured this out. Very simple. You go to Google and you say set as default. If you're like me, you say Blasingame data. Oops, Mr. Churchwell can't see this. Sorry about that. And up pops this little stupid menu. You click there. You go to P620, and here's everything we've got tonight. So here's the base lecture that I was talking about. Here's the working lecture. Here's tonight's lecture. And then there's the syllabus, and I gave it in. This is obviously a draft because I already got a screw up and I'll have to fix it. But I'll do that tomorrow, and I'll tag it with a different date when I fix it. This will be your course file location, so anytime you want anything, it'll be here. I made a note in the contacts that I always want you to contact me by email. I mean, this is kind of the most important thing. I've also got a protocol for doing that. Ruben's probably angry at me because I made him do his twice or three times. There's roughly 30 of you in here, and then I've got another 30 graduate students. I have this protocol where you give me the date, you give me your name. I'm one of those people that never throws anything away. So tonight or tomorrow, I'll create a folder for all of you, and everything that you correspond with me will go in that folder. And the way I track it is, as Ruben knows, by name, date, etc. And Alex hates it. Andrew hates it. I'm sure anybody else who, David, I think you hate it. But it keeps me sane, and me being sane keeps you sane. So what are the goals of P620? We're going to start with a mathematics review, and I apologize that I'm not a very good math teacher. I'm not a very good teacher at all, but I am a really good taskmaster. In fact, I'm an outstanding taskmaster, so I'll drive you to learn. This review will include probably some recitation work with Alex periodically, especially the math stuff. If you're afraid of math, then you're in the right place. If you don't like math, then you're in the right place. If you don't want to learn math, you're probably still in the right place, but you're going to probably learn a few things as we go along. We'll have 5 review lectures on math, and then we'll start our sequence of lectures on petroleum engineering. And then, as I say, we proceed to the empirical areas of geology and petrophysics. That's petrophysics, of course, is rock properties. and then on to building blocks of reservoir engineering, permeability, capillary pressure, relative permeability, electrical properties of rocks. I know you're going to look at some of these lectures and they're going to be old, and yeah, I know I should go back and clean them up and write a book and everything, but this way you get the experience of me, not some stupid book. So you're going to have an opportunity to work with me, go through the same kind of thought process I had. Those of you who've only worked in the metric system, that would be the French guys, right? Yeah, you're going to hate uh, the American system of units. That's okay though. I'm sure you'll adjust. And there will be some conversion factors and things like that. I was working on a project in Mozambique a few years ago, and as we began lecturing, I had the drilling guy go first. He was talking about, uh, whatever it was, 4.5-inch drill pipe with some other specifications. And this young man stands up and says, "Stop speaking, Professor." And we were all like, uh-oh, what's about to happen here? And in Mozambique, because it's a socialist country, students have the right to strike and everything else. And people you could see the Mozambican faculty were like, what's he going to say? What's he going to do? He says, we refuse to work in anything but the metric system. And there was this really long pause, a long, quiet, sort of everybody getting their feelings, adjusted. And the drilling guy just goes, well, you're going to have a hard time finding metric drill pipe, metric drill bits, metric, this, metric that. And he goes, well, we refuse to work in non-metric units. And he goes, well, I think for today, you're just going to have to accept that, you know, uh, a lot of petroleum engineering is not metric. And in particular, almost everything involved with drilling is non-metric. And eventually sort of things settle down, and I think they kind of got the hang of it. They understand that there's a standardized set of units. Uh, I don't know what to tell you. I know some of you are going to hate PSI. I know some of you are going to hate barrels and things like that. But unfortunately, those are the units we work in. For example, why do we work in volume? Why don't we work in mass? How many of you are chemical engineers by training, if I may ask? Yeah, I forgot about you. That's it? Just one? Wow. Okay, so why do we work in volume instead of mass? Hmm? You want to pass it to someone else? Anyone else want to answer? Why do we work in volume instead of mass? We sell it in volume. That's the easiest and most quick answer. Okay. So is a barrel of oil a barrel of oil? Is a barrel of oil from, I don't know, Athabasca or, some really nasty place? I'm trying to think of where a really good heavy oil would be. Maybe California. There's some really ugly heavy oils in Texas that have a huge discount. They're basically giving them away right now. Is that going to be the same as West Texas Intermediate or Brent or Saudi Light? No, because those are all based on the quality of the product and what they can be, or the quality of the base, which is the crude oil. So I think everybody understands that, but I could still remember people in chemical engineering saying, you dumb, stupid petroleum engineers, why don't you work in mass? I know the Russians work in mass. I think China, you work in mass as well, a little bit, but you end up having to keep converting back and forth because your system isn't internal. You're buying barrels, but you're moving tons. I get it. But at any rate, just be prepared. Sorry I went off on a tangent. I'll do that a lot, but we're going to work in the units that have evolved, not the ones that we necessarily want to. We'll then derive, or maybe I shouldn't say derive, but we'll work with Darcy's law. We'll work with non-Darcy flow as well. These came primarily empirically, Darcy's law through some work by Darcy. He was a sanitation engineer who was looking at filtering water in Dijon. And then non-Darcy flow through the Forkheimer equation and other parallel relationships to that. And then we'll talk about material balance. Again, we only have one chemical engineer. So chemical engineers live or die by material balance. That is that you conserve mass. Then something called pseudo-steady state, which is as it implies, it sort of looks like steady state, but actually things do change with time. There's probably a better definition of that. Generally speaking, in applied reservoir engineering, we call it boundary dominated flow, but that's okay. For today, you can call it pseudo steady state. The diffusion or diffusivity equations, which are very familiar to anyone who's worked in any engineering discipline, whether it's heat, electricity, again, mass transfer, chemical engineering type problems, um, flow of fluids and pipes, that sort of thing. They all have the same foundational types of equations. We'll spend a bit of time deriving the diffusion equations. A lot of people stumble here. They're tired. It's sort of mid-semester, and they don't like the diffusivity equation. And I want to explain that all this effort we spend on deriving the diffusivity equation is really so we can develop a fundamental understanding of all the things that it applies to. For example, some 20 years ago when I was teaching this course, I had a young man who had an emotional breakdown when he suddenly realized that the diffusion equation that we had been deriving in class was the same as the equations that they had been programming for reservoir simulation. And to us, it's obvious that it's the same foundation, but to people who haven't worked in the mathematics side, he had a moment. It was a joy to be there. Let's just put it there that way. Then we work towards the reservoir engineering solutions. Generally speaking, I'll keep it simple. We'll look at radial systems, linear systems, hydraulically fractured wells, naturally fractured systems. We don't talk a lot about horizontal wells in this course, primarily because your instructor is not the brightest bulb. I really am not a horizontal well type person. I've had a lot of students who've worked on nice horizontal well solutions. I have one now who is. Dr. Oscan's dissertation is included in your reference reading, which I'll load later tonight. If you want to learn sort of ground up on that sort of thing, that's something you can use. We're going to make some project assignments or homework assignments. Alex and I have been discussing this. We kind of like to do this in steps. It's not exactly the right time to bring this up, but let me say it this way. I don't care what product you use or what system you use. I don't care if you use an abacus or a calculator or you use Mathematica or MATLAB or C++. Today I mentioned Fortran, and Alex asked me something about rubbing sticks together and making fire and all this other stuff. But that was what I was raised with, so I'm very literate in Fortran. I did try to program in Visual Basic, but every time Windows changed and Excel changed, all of my things stopped working. So I'd probably say that if you can program, how to print the time in Visual Basic, you're doing better than me. But Visual Basic is an option. Mathematica is an option. MATLAB's an option. All these are supported here. Just a quick down the track here. Favorite computational tool? Okay, I didn't put that on the list. No, Python's fine. MATLAB? Ah, good. Sorry? Or either one? Neither one? Oh, you never programmed anything? This is going to be a fun trip. Yeah. Wait. What was that again? Okay, we know. Okay, so if you need a MATLAB tutor, he's sitting in the back of the room. There's only one person in this room that uses Mathematica? Wow. Wow, that is amazing. How many people are going to prefer MATLAB? Looks like somebody better learn it. That means me. How many VBA? There were about half a dozen or so, right? Yeah. No Fortran? Okay, I got it. You're going to be expected to debug your own code. I mean, you can come to Alex or me, and I'll probably be looking at it like this, and then like that, and that sort of thing. But going ahead and get in your mind how you're going to want to solve problems. Uh, I guess we could have some Laplace transform assignments. Historically, the last couple of years, we've had a Laplace transform assignment. We've had special function assignments. By Laplace transform, what I'm saying is you invent your own inversion algorithm. And I know all of you are going, it's not that bad. If I can do it, you can do it. And I don't expect that anyone is going to come up with something that's going to work better than the primary algorithm we use, which is the Stayfest algorithm. Stayfest is easy, it's predictable, it's oftentimes not as accurate as you'd want to be, but if we use Mathematica, we can set its precision much higher and so forth. Do you have precision ability in MATLAB for Mathematica where you can achieve very high precision? I'm not really buying this, but okay. Right, right. Yeah. And that algorithm is really designed for computational rigor. You know, it provides if you're willing to push it to the breaking point, it'll provide extremely accurate results. And I know I keep saying Gaver Stayfest, but there's another variation of the algorithm that he references, but it's still sort of a similar basis. It's a sampling algorithm. Special functions, most special functions are in Excel. There are a few that are not. Ironically, one of the ones we'll use the most, which is the exponential integral, is not in Excel, but it's relatively easy to program. Correlation of petrophysical data is sort of a personal favorite of mine. Most people don't like it, but you know, it's worth learning, worth trying. Capillary pressure, relative permeability correlations, that's another sort of favorite of mine. Material balance, I think when we get to material balance, you're probably going to find that, well, excuse me, while I think it's really important as a learning event or as a learning exercise, the use of material balance in practice is pretty small. Pseudo steady state flow, that's another one of my favorites, and we'll spend quite a bit of time on that. Sometimes I'll ask you to derive the pressure squared solution for pseudo steady state, and people forget that the square of the what is it? The integral of the square is not the same as the square of the integral, and you know that's tricky. I shouldn't give you tricky problems, but sometimes things like that happen, and you know I probably won't, now that I've given away the secret, I probably won't give that problem again. But it's a relatively simple problem that gets really ugly really fast. Radial flow solutions are really popular. I like to give the constant pressure rather than the constant rate. We spend all our time solving the constant rate solution, and then I can trick you, not trick you, but switch the problem around by solving for constant pressure. Linear flow, fractured well cases, dual porosity reservoirs, convolution and deconvolution, and then wellbore storage. Is anybody in here a mathematician, mathematics major by training? Yep. Okay, so convolution is a forward process, deconvolution is a reverse process, right? And have you studied deconvolution at all? Yeah. So it's a holy grail. If we could do deconvolution, then our lives would be much better. We would be able to interpret the behavior of things in reverse. It's sort of the secret ingredient to, I don't know, whatever the Lord of the Rings or something like that is. I got to try to be your generation. I could have said Star Trek or Star Wars or something like that, but it's any rate, it's come along in the late 60s, then in the 70s, then in the 80s. I've written my dissertation on deconvolution. I've had several students work on deconvolution. There was a big resurgence on deconvolution in the late 2000s, and then a few little things, but it is basically a solution in search of a problem. The dilemma with deconvolution is that the data has to be excruciatingly accurate, otherwise the errors just compound and exponentiate. But it's a great thing to look at. Convolution is a little bit more straightforward. And then last but not least is wellbore storage. Wellbore storage is kind of a fun problem, but it's like taxes and death and everything else. You're not going to get rid of wellbore storage. It's a chronic condition. And for those working in pressure transient analysis or who have ever heard of pressure transient analysis, wellbore storage is where you couple the wellbore with the reservoir, but all the flux comes through the wellbore, so it acts like a dampening valve on the reservoir response, and it can be very I'm trying to think of a polite word, distorting. It has there's some rules of thumb and some other things, but really the only way to eliminate wellbore storage is to reconfigure the wellbore while you're testing. And Schlumberger will sell you a tool that'll do that with something like $10,000 a day. So you have to decide how you want to play that game. I was really impressed by Thomas Edison, or inspired by him as well. He, when asked, that he used 10,000 different experiments to determine the filament for the light bulb, and he said you wasted all your time doing that, and he said no, I found 10,000 things that didn't work, and I like that. That's never give up kind of thing. Some important rules for life: never own anything that eats while you sleep. I had a talk with someone the other day that wanted to buy their daughter a horse, and I reminded them of that. Never own anything that needs to be repainted. I just had a contract let on my house here that I need to get it repainted because the guy didn't do a very good job the first time. Never own anything you can't drive a nail into. I don't really know what that means, but somebody used to say that a lot, so I thought it meant something. Maybe it means don't own anything too fancy. But I don't think you would drive a nail in your car. Maybe, I don't know. Always work harder than those that you work for. So I'm going to work harder than you are here. And then if you have to herd cats, it's best to be a rat. So, that's sort of my philosophy too. And then I try never to say no to anything. Sometimes people put me in a corner where I have to say no. So just, if you make me say no, I will. Some guidance on this. This is graduate school. The only person that you're competing with is in the mirror. Right now, I would expect everyone in this room to do extremely well in this course, but that's your choice, not mine, not Alex. We're going to provide assistance. We're going to provide guidance. We're going to provide whatever resources we can. I encourage you to work together, but also to mix up a bit, to get to know everyone in the group. But again, the only person you're competing with is you, so just do your best work. And really, that's my commandment, is that you must, when you submit something, I want you to pretend that, you're submitting it to, I started to say God, that would really be inappropriate, but your mother, okay, that you're giving something to your mother, your grandmother, and that this really has to be your best work. The focus is this is an essential course in reservoir engineering. I really think, that for those of you that are willing to take this course, I think you're going to get compound value out of it. The material is very dense. Don't underestimate the workload and the timing. Most of the time when we were having issues, it was generally the distance learning students. We only have one, and that was because they were working. But this material is really dense. The material will teach itself, but you have to really put your heart and soul into it and work on it. And again, I'll be around. Alex will be around. I am here to help, and I will answer any and all correspondence. I put relevant there. I do answer irrelevant correspondence as well, but it'll be quick, like, I don't understand. And actually, I had a couple of those this weekend. Someone from a university in Iraq wanted to posed a question that was just almost absurd. It was, how many golf balls can you put in the wellbore? And I was like, what the hell is he asking me this question for? And I mean, I'm exaggerating. That wasn't really exactly what it was. So I tried to be polite and say, this isn't my area. And, he's like, well, you're a professor. And I said, well, why don't you go to your professor and ask him to help you form the question better so that I can help you answer it? And he goes, it's not for me, it's for my friend. And I was like, oh, God. I just said, okay, I respectfully terminate the discussion, and hopefully your friend will figure it out. So this is the syllabus. I know it's also packed in there pretty small. There's about 10 books that are 8 of which are online or will be online as soon as I put them there. The ones in red you'll need to buy if you can't borrow or steal one. The rest, which are the optional text, they're down below. Nobody's going to buy them, but you could go to the library and borrow them. The two at the bottom, the asymptotic approximation of integrals and the asymptotics and special functions, are just absolutely unbelievable. They're fantastic books. Also Bender and Orzog, that's 9, 10, and 11 on the optional text, but Nobody's going to buy those. Then there's a bunch of stuff about policies, and I have to put all this in here so that, I protect everybody. You're resident students, so you need to be in class every time. We'll give David a pass periodically, but because he's commuting from Houston to be here, and there are probably others of you as well. But I do expect you to be here as much as possible. And let me rephrase it because Alex is probably gritting his teeth. I expect you to be here. If I'm here, you should be here. We will have a few online lectures due to my travel, and I'm not going to sugarcoat it. I've got some ugly travel with SPE this year. I'm on the board. I'll be out the latter part of September, and then other parts of November with some SPE travel. So I do apologize for that, but the way we'll fix that is maybe we'll double up and we'll do a Monday, Tuesday, Wednesday, Thursday type thing when I'm in. But you will not suffer for my being out. On the top of the second page, there's this text about you must show all your work, you must show all your calculation steps and everything else. There's a reason for this, and that is that some of these problems are really hard, and I give you a lot of the detail on them, but sometimes there's not the secret ingredient is missing, and I need you to tell me what that is. A famous problem like that was the case of the hydraulically fractured well in the Laplace domain. That solution was derived by Jose, Horn, and Ramey. Very nice, very elegant solution. And then Ragavan and Ozcan came along later and said, oh, here's a way to make it even better. And they showed a nice little fix, integral transform that did some nice things for that. But that solution was never demonstrated, either the Jose, Horn, and Ramey or the Ozcan-Ragavan solution. It was never shown to be equal to the Gringarten-Ramey-Ragavan solution, which came like 20 years before. And so you're looking at a solution in the Laplace domain, you're looking at a solution in the real domain, and if you were to calculate them, they would give you exactly the same numbers. But what I want you to do is I want you to take the solution in the Laplace domain and derive the real domain solution. And it really wasn't that hard, but there was some kind of ugly integral transforms that needed to go in there. Obviously, since I've told you about it, I doubt I'll give you this problem, but we might. And, those are the kinds of things where you need to show all your details. Some of these Bessel function solutions are going to look really ugly, but I think you'll get to the point where you'll realize Bessel functions are just, and any special function actually, is just sort of a suitcase for whatever its definition is. There's usually an integral definition, or maybe even a derivative definition, or a series of integral definitions. There's some Bessel functions that have like triple integral definitions and that sort of thing. But you can define them in such a way where you're just sort of carrying them along. There's some mathematical operations that you can perform on them that are fairly straightforward. Again, I just want you to show all your work. Tonight, Alex and I put some comments in about plots. Some of you seem to think it's okay, and I know the online person won't see this, but to put your graph in the corner like this of the page. God gave you the whole page, so let's make our graphs really big, so we can read them. And let's put these things called labels where it says X and Y and title, and that sort of thing. I know it's pretty silly, but some people don't seem to understand that. There'll also be some discussions about how to make figures and how to interpret trends, but that really won't be much part of this course. That's more for analysis things. There's a statement on scholastic dishonesty. Everybody knows they have to behave, and I've already told you that I want you to collaborate, but you can't collaborate whenever I tell you not to, and I think everybody knows that as well. The work standard is I really want you to give me your very best work. That seems to be a bit of a, I'm trying to think of a polite way to say this. People don't take me seriously on that. I mean, you're here. Impress me. Show me how smart you are. I'm challenging you. Feel free to beat me. You can do this. You can give me some work that will really impress me. And some of you will decide you don't want to do that. So hopefully you do. There's an email protocol down below. I apologize if this insults your intelligence, but you can see it down here. And of course, the syllabus is full size, so you'll be able to read it. But please use this form. Again, I'm sure Andrew, Ruben, Alex, you all hate me in your sleep, but this way I can keep track. And I put down at the bottom that I'd like to have a phone number as well, so that if I do need to text you or we need to talk, I can get in touch with you. But I would never call you unless it were an emergency without sending an email or a text. You can also see my guidelines on how to respond to emails. When I send something from eCampus, nothing makes me crazier, and I'm pretty crazy, than for you to reply to me using the eCampus thing. Because have you seen the eCampus subject lines? They're like 300 letters long. And then you're going to send it back to me, and I have no idea what your question is. I just know I've got this huge, ugly email. Down at the bottom, we talk about computational tools. We've already decided Visual Basic, MATLAB, Mathematica, programming languages, etc. I forgot about Python, sorry. Okay, you're responsible for how you want to compute things. Next is a list of topics in sort of sequential form. First, we'll go over mathematics, then we'll go over petrophysics, then we'll go over fundamentals of fluid flow and porous media, and then we'll start deriving the classical reservoir solution. We may cover some other things like multi-layer reservoirs, dual permeability systems. We don't usually get this far, but these are still topics that we may ask. Things like radial composite systems or models for flow impediment, which would be time-dependent skin, or some other dependency of skin. I've done quite a bit of work with that. There could also be some other extensions, as you see down at the bottom, of different kinds of problems. Maybe I did try once to let everybody have their own final exam problem where you choose it and you tell me what you want to do. And the classical word for that was disaster. But, I don't know. Maybe we could try something like that where you have an individualized project. I'm absolutely fine with that. You can see the list of lectures on the right-hand side. And I did put a disclaimer down at the bottom. I called it a legal disclaimer that this is subject to change, and it will. We're going to cover everything. That I promise you. But there is a possibility, if not a probability, that the schedule will change. All class sessions will be recorded, just like this one is. They'll be on eCampus via this device, and I will drop the videos on my website sometime in the evening after we copy them. I make a WMV file. It's relatively small, although it is larger than some people would like. I don't think you ever had an issue with it. You didn't mention it, but somebody in 633 was telling me they were having problems with file size, so I was zipping them, and they were also having continuity issues. But unless I have to start doing that, I'd prefer not to. So just between us, I probably won't. I'll just leave the raw WMV file there. We'll also have as needed classes. I thought about having one tomorrow night, but I think everybody's pretty tired with all the excitement of the first week, so we'll just meet again on Wednesday. That's about it for the schedule. You get Thanksgiving Day off. Congratulations. Is anyone here going to the SPE fall meeting besides Han, you and I? Nope. In Dubai. Yep. Yeah. So we're not going to be here. So we'll have to work on the lecture schedule that week, and actually maybe the week before, because I have to go for the SPE board the week before. But we'll work on it. There's some information about students with disabilities, and then the Aggie Honor Code, and some copyright stuff. On your assignments, and we'll give you the sheet to do this, you'll see something that has this Aggie Honor Code thing. It's just a cover sheet. It'll go on each assignment. I'd really appreciate it if you would put your cover sheets on your assignments, and again, we'll include them in the assignment files themselves. This is just an example. Now we start looking at the modules, or how we're going to cover the material in this course, and I'm not really sure. We've got about 26 minutes before class is up. If I go into the detail of what I want to cover here, I'm afraid I may scare you off because, there's another 9 pages describing all the things we're going to cover in the syllabus. Let me take a pause moment. I'll have a drink and you talk amongst yourselves. Do you want to see 9 more pages of the syllabus or do you want to read it on your own? And you know the answer. Okay, very good. Pass the bucket around there, Mr. Burkhardt. Ms. Zinят, what do you think? Should we keep going? You think yes? You're paying my time, so I might as well, right? Okay. So she said yes. She's the first person in the class. Mr. Churchwell's online. Where's Mr. Yang again? Ah, okay. So you want to keep going too? We'll go opposite spectrum of the alphabet. Or you want to quit now? Yeah, good answer. Okay. So the first thing we'll do is go over a few things in algebra and trigonometry, partial fractions, factoring of equations, and so forth. This is one of those places where Mathematica is truly outstanding. I don't think MATLAB does symbolic manipulation, does it? It does. Oh, okay. Is anybody an expert in MATLAB and know how to use symbolic manipulation in MATLAB? I think that's Spanish for it's not as good as Mathematica. Okay, I'll buy that. And then we'll cover the polynomials, exponentials, logarithms, trigonometric functions, special functions. The error function, the gamma function, the exponential integral, and Bessel functions are of our primary interest. How many of you guys like history? Yeah? Okay, we got some history buffs. So Chebyshev economization, what does that mean? What is it? What is a Chebyshev polynomial or Chebyshev economization? Does anyone remember? It's where we substitute Chebyshev polynomials into an expression and then factor out the higher order terms. And in theory, we should achieve the same error with less terms in a polynomial. And I know you're all going, so what? Well, that's why you got to learn old things. Maybe there's some value in doing a power series expansion or a polynomial expansion for something that could come from a Chebyshev expansion. But I'll show you some very simple cases that you don't get something for nothing. You may get a little more uh, behavior or more consistent behavior out of a Chebyshev economization, but you're going to lose something somewhere. It's kind of like a seesaw where you give one place, you're going to lose it another. So we'll do some examples of Chebyshev polynomials. They're very exciting. I can tell you're all really thrilled. But when people were first coming up with computer algorithms, what operations did they have at their disposal? What does a computer do? What does it calculate? It does addition, it does subtraction, it does multiplication, it does division, and what else does it do? It does a logic check, a true-false check. Okay? How does a computer calculate an exponent? So you don't know. Well, if it's an integer, it just multiplies it times itself, however many times the integer is. How does it make a real exponent calculation? Do you know? He uses logarithms. Okay. How do we calculate a logarithm in a computer? Somewhere there's a polynomial because the only thing we can use is addition, subtraction, multiplication, division, okay, and logic. Next, we'll talk about the numerical integration and Taylor. Well, first it'll be Taylor series expansions, and then numerical integration. We'll derive trapezoidal rule and Simpson's rule. And then we'll talk about Gaussian quadrature and Laguerre quadrature. All of these are historical methods. There are millions upon millions of man years or people years that were invested in this. in the 40s, 50s, 60s, trying to come up with ways of making computer calculations. And now you look back and you say, you guys were crazy. But Laguerre quadrature can be used to invert Laplace transforms. It's not very efficient and it's also not very effective, but it can be used for that. And there is a way of deriving inverse Laplace transform formulas from Laguerre quadrature. And there's also ways of taking Laguerre quadrature and calculating Laplace transforms. So we may do some of that. Then we talk about how to calculate finite difference derivatives. And I confess, I don't do a lot of this. It's really just to show you that for analytic functions, you can estimate derivatives at a certain order of accuracy, first derivative, second derivative, third derivative, fourth, and it's all based on function evaluations. As I mentioned, the next thing we'll do is derive the trapezoidal rule and Simpson's rule. These are both in a text that I provide the full detail. Then we'll talk some more about Gaussian quadrature. Gaussian quadrature allows you to evaluate a polynomial f of x from the limits of x0 to xn using a summation formula. And obviously, the more summation terms you use, the more accurate it becomes. And there's something called a weight, which is given by a w, and an abscissa, which is given by the z value. And those are evaluated from a book. Those are the roots of the polynomial that were used for that. So, there's going to be a book in Abramowitz and Stegen, which you'll get a copy of. There's a few cases. I don't remember how high the value of n goes, but there literally are people who spent their entire career on calculating the coefficients for the Gaussian quadrature. Same thing with Laguerre quadrature. It's just a different integral. I don't know if you can see it well enough, but the Laguerre quadrature looks, smells, and tastes like the Laplace transform. Hence, it can be recast into a form where we can use it to evaluate the Laplace transform of a given function or even of data if we wished. Next is first and second order ordinary differential equations. Some really simple things like classify the order of a differential equation and then verify a solution by substitution. I want you to be able to derive the method of integrating factors, which is a direct solution for simple first order ordinary differential equations. And then, some simple numerical methods, the Euler method or the Runge-Kutta method. When I was first teaching this course, I was really in love with the Runge-Kutta approach because it's a self-starting differential equation solver. So, I thought that it would be really useful. But of course, self-starting means that you have to have some finite span of how you're going to calculate it. There are some adaptive methods, but the Runge-Kutta methodology was derived with a constant delta x type evaluation. Again, there are some methods that you can use to enhance and accelerate that. But these methods, things like Euler's method and Runge-Kutta method, have relatively narrow applications within petroleum engineering, although they have been used for things like calculating Muscat's or Tarner's saturation pressure equation, which is a material balance type formulation. This was done back in the 40s and 50s, or this was derived back then. Solution of first order ordinary differential equations, again, deriving integrating factors, and then solving these equations using integrating factors. Second order ordinary differential equations, of course, this is what we're really interested in. Although we're not interested in ordinary differential equations, we're interested in partial differential equations. But there's a nice thing on the horizon, and that thing on the horizon is called the Laplace transform. When we take the Laplace transform of a partial differential equation, we obtain an ordinary differential equation in the Laplace domain, and then we can use ordinary differential equation methods to solve it in the Laplace domain, and then, of course, we take that solution in the Laplace domain and we invert it back out. But right now, all we're talking about is how to solve second-order ordinary differential equations. So we look at the homogeneous part of the solution and then the particular part of the solution. And you can use all sorts of different methods to solve second-order ordinary differential equations. The best method to solve a second-order ordinary differential equation is by inspection. And we will we'll study the different differential equations, Bessel's equation, Legendre's equation, Matthews' equations, etc. And those will tell us, what the solution is by inspection. Next is a discussion about the Runge-Kutta method, and I'll leave that for when we lecture on it. But essentially, the Runge-Kutta method is a methodology that you set up your differential equation in a certain form, and it allows you to solve it directly, taking small steps. Now, the Runge-Kutta formulation has a relatively unique scenario that if you evaluate it in a certain way, it simply becomes Simpson's rule. So that'll give you some idea of the accuracy of the base formulation of the Runge-Kutta formulation. There's a hand calculation for both the first order and second order in the notes, and there's some some cases that we could study if we want. Now we get to the Laplace transform, and we really should spend about a month on the Laplace transform, but we're probably only going to spend a couple of lectures on it. I know most of you probably hate the Laplace transform. You even hate the word Laplace transform. How can I best describe the Laplace transform? I used to talk about the Laplace transform like getting married. Anybody married? David, you are. Anybody else married? Yeah? Did you wait a long time before you got married? Yeah. David? About a year, yeah. But if you wanted, you could just go to Las Vegas and get married, right? So getting into the Laplace domain is like marriage. You can get in really easy. Now, anybody in here divorced? Okay, that's getting out of the Laplace domain. That's pretty tough. And so the way we usually get out of the Laplace domain is we cheat. How do we cheat, class? We use numerical inversion. Trying to cheat or trying to solve Laplace transform analytically for book problems and that sort of thing, that's great. But for real problems, mm-mm. How many of you were trained as electrical engineers? Anybody? No, that's good. I won't torture you too much, but if you were, I would say electrical engineers have all these Laplace transform problems because they set their circuit up. They know it has an answer. But us, we don't have that luxury. Our problems cannot be solved directly from the Laplace domain. We have some very complicated relationships that arise. And later in the semester, when you see them, the first reaction you'll have is, this is awful. I wish I hadn't taken this course. This looks ugly. And then we start talking about the characteristic behavior of those Bessel functions. And this piece times that piece eliminates it. This piece has a relationship with that piece, eliminates it or reduces it to something else. And pretty soon we're left with something that's relatively simple in Laplace domain. And I'll go to my last slide in a couple of minutes and explain what that means. But, I'm not going to leave you in the Laplace domain. Dr. Holditch, he used to torture me all the time and say that I loved living in the Laplace domain, and he made fun of it. But what you can learn by solving these reservoir engineering solutions analytically is their limits. Okay? How, the assumptions that go into them, how they behave, why they behave, how to break it, essentially. Now, several of us in this group probably know there's a software package made by a French manufacturer, and this manufacturer is really pushing to eliminate analytical solutions from the domain. They have both an analytical solution and a numerical solution, but they know they can't do that. They know that people, as well as the methodology of solving it, you're going to want to have an analytical solution to test against it. And if sometime you want me to show you, I can take a data set, I can match it with an analytical solution. Obviously, it'll be extremely fast. And how do you describe an analytical solution? It's an approximate, it's an exact solution to an approximate problem, whereas a numerical solution is the opposite because we're solving it approximately, but we're defining it exactly. And so here, the reason we're focused on the Laplace domain is our problems just happen to be extremely well suited for Laplace domain. Name a condition. Radial flow, linear flow, horizontal wells, horizontal multifracture, all these different cases, they all have Laplace domain characteristics or characteristics which are suitable for it. And then, whatever the force is in the universe, saw fit to allow us to use convolution, mathematical process. What is convolution whenever we go to Laplace domain? In the real domain, convolution is an integral over the entire time span. What is it in Laplace domain? It's a multiplication. Okay. Now, like I said, it looks like you want to get married. Think about this. Because once you go into the Laplace domain, you got to get out. And when we do the discussion on the Laplace domain, if I have a pen, maybe I'll draw my favorite, being a boy from southern Louisiana. I always talk about a crab trap. And in South Louisiana, we put a little something in the crab trap, and the crab goes, "Ooh, I want that," and he goes in, and then he can't get out. That's the whole point of a crab trap. So that's like the Laplace transform. So then, how does he get out? He uses a bomb. He blows a hole in the side of the cage. Except if you don't do it right, you're having crab soup that night. And you have to really be careful with numerical inversion because you have to test it for different parts of the equation. Sometimes it doesn't work, even with extremely high precision solutions. Okay, enough about Laplace transform and how sexy it is and how wonderful and how it's going to change your life. Now, very quickly, you see there's a stair-step function, and then there's some other summations and things like that. The Laplace transform can be applied to a table of data. You can take discrete numbers in the Laplace domain. Laplace transform is just an integral, so you apply the rules of integration over that, and you can take a data function in the Laplace domain. You may be thinking, who cares, Tom? Remember what I told you, that a summation in the real domain becomes a multiplication in the Laplace domain. So there may be a real value for doing this. There have been a lot of people that have tried to work exclusively in the Laplace domain for computational problems, and sometimes that hasn't worked out so well. The other thing that Laplace transform does for us is, like I mentioned, it converts a partial differential equation into an ordinary differential equation. It converts an ordinary differential equation into an algebraic equation. So this sounds like alchemy. It sounds like we can take a problem, break it down into its pieces, and then put it back together however we want. And for the most part, that's true. But again, in petroleum engineering, as opposed to things like mechanics and electronics and other things, our problems are not so well defined. So, we don't often get something that just comes right back out the way we wanted it to. So I'll leave it at that for the moment. We also have methods for inversion of Laplace transforms. If you're looking down in the lower bottom right hand corner, I described a methodology for taking the Laplace transform using Laguerre quadrature. There's that formula. That way you could take the Laplace transform of a function or of a data set, and I give you some guidance on how to do that. We can also take the so-called Gaver formula and invert using the Gaver or the Witter methodology. And then down below, we start to see what's called the Gaver and Gaver-Stayfest algorithm. And this uses a sampling function. It samples the Laplace transform, or samples a function in the Laplace domain, and it allows you to make an inversion based on those sample calculations. This is the algorithm most of us will use. It looks horrible, but it's actually really simple. If you program it once, you'll never forget it. Again, those VIs that you see down here, this god-awful looking thing, is really just a bunch of numbers. You can easily set that up as a calculation, and I have a table of what those coefficients are. Stayfest probably deserves, the Nobel Prize of mathematics or something for coming up with this, and he did it in a really short paper. Gaver spent all this time deriving the statistical background of why this sampling function works for the inversion of Laplace transform. And then Gaver comes along, and I mean, it was a magnificent piece of work. And I know I'm up here being really enthusiastic, and you're like, we could go home. We could, the bus is going to stop running. Will this guy ever shut up? Take another drink of Red Bull. But Gaver, he figured out how to make this thing work. But he did not understand that he needed an extrapolation formula to solve this. His algorithm requires that you take the number of samples to infinity. And Gaver just looks at it and goes, oh, use a collocation polynomial. Wow. It's like you have a Maserati that's missing a wheel or something, and Gaver comes along and goes, oh, or maybe you forgot the key or something like that, and somebody comes along and says, oh, it'll run a lot better with this. So he really deserves a lot of the credit. Next is special functions, and I'll stop after that because we're at 9 o'clock. Special functions, again, we'll use the exponential integral, the gamma, and the incomplete gamma function. Incomplete gamma function doesn't show up often, but where it does, it's usually the integral of some sort of a power type function. The error and the complementary error functions, those show up quite a bit, but mostly in linear flow type problems. Bessel functions, the J's and J1 or J1 and J2, or sorry, J0, J1, Y0, Y1, those are generally solutions of radial flow problems or radial problems when the solution is computed in the real domain. There was a fellow by the name of Muscat who was a physicist. He worked in the 30s and 40s. If he'd have had a computer, none of us would be here because he figured out all the problems then. He just didn't have the computer to solve it. He did not work in the Laplace domain. He worked using separation of variable type solutions. He also, being a physicist, kind of solved engineering problems a little backwards, but that's okay. He deserves all the credit we can give him. In fact, he lived to be very, very old and, was still quite aware, I think, of what he had done. We use modified Bessel functions in the Laplace domain, and those are the ones that are I0, I1, K0, K1. And you're all going, well, what is I0? I0 is kind of, it goes up, looking from your perspective. K0 comes down. K0 is kind of like a logarithm. It actually has a logarithmic approximation. K1 is kind of like 1 over x. And I0 and I1 are kind of like polynomials or exponentials that come off of 0 or 1. But we'll talk about how to derive them, how to interpret them, how to manipulate them, and so forth, that being the Bessel functions. And then we'll talk about Bessel's differential equation and Bessel's modified differential equation, which is down in the lower left-hand corner of the page. And I can assure you that you're not going to have to learn much about Bessel's differential equation. You're going to have to learn a lot about modified differential equation. And I think with that, since we're at 9 o'clock, we'll stop. We'll pick up a little bit more on this on Wednesday, and then I think, Alex, probably be a good idea for you to do math recitation next week, if that's okay. I mean, you'll have to record. You'll have to get Ted to set it up. You can do your own. Sorry? Yeah, but I want you to be able to communicate with the students, so I want to make sure you're on eCampus along with me so that you can do. Homework 0 will be distributed probably tomorrow. Homework 0 is a freebie. I need you to. It's a resume assignment. I'll give you a template that I like. I know some people don't, but what I want you to do, it's just for me, so that you fill out this resume and tell me a little bit about yourself. It has to be one page. Don't go crazy like I did and make it 8-point font. 9 points probably as small as you want to get, maybe even 10-point. David, you hire for your company periodically. Somebody hands you an 8-point font resume. I'm sure it's just going to go right in the shredder. But the purpose of this is to inform me and to motivate you. You have a resume workshop this weekend, right? And then it's tomorrow? Oh, there you go. Okay, so I'll try to distribute it tonight, but I'm kind of starting to get tired. But maybe certainly you want to work on this. You want to have some ideas about how you want to present yourself. I'm not saying that there is a recovery has begun, but I think we are, at least at the beginning of the end of the downturn, and things are stabilizing. There's still going to be some trauma, but at 97 million barrels of oil a day consumption with less than a million barrels a day swing, I think, I don't think jobs are going to be a problem in a couple of years. And I think, if you'll learn what we teach you, try to focus on, things that add value, you're going to be pretty happy. I think this is a good time. Alex, anything else you want to share? David, anything you want to throw? David and I worked together on a project a while back, and I think David probably killed me in his mind about every way you could. I made him start over and rework all of his math from basics and so forth. And I'm telling the story from my perspective. Feel free to jump in and tell it from yours, but he will never send an email asking for help to me again. I don't think. Yeah, but I think those are the kinds of things that build strength. And you're not going to get better by doing everything yourself. You're going to have to work with other people. You're going to have to get input from other people. And if you ask me for help and I can't help you, I'm going to try to find someone that can. But in your case, you just happen to find the right person at the right time. Any questions before we break? Doesn't look like the candy bucket made it very far. Why don't we pass it around one more time while I shut down? And
I just add on to your comments on employment. I do strategic planning, so we look at price decks and whatnot. Like last week said, looks like the downturns are mostly done. Most banks are using strip prices that rise into the high 60s at the end of next year. Gas prices look like they're coming back higher than they've been in several years now, hitting somewhere above $3 next year, maybe mid threes by the end of 2016. So I think people like working gas a little better. It's nicer, cleaner data, so it's always a plus.
I understand that those of you who are new to this may not fully appreciate how far we've fallen, but this has been the worst downturn I've ever experienced, and probably because I've seen its toll on legacy knowledge. There's going to be a lot of people that are gone from the industry. You need to start working your relationships now. You're the next generation of leadership, but that's almost irrelevant if you don't have the skills that you need to do your job. So focus on that. And we can tell you all day long that things are getting better, but we understand that it's still a challenge every day to focus on what kind of work you're going to do, thinking about where your career is going to go and so forth. But at 97 million barrels a day and going up, I don't think you're going to have to worry about employment over the long term. The estimated peak oil rate, I guess, is 120 million barrels a day before sunshine and wind take over. But, our job, by the way, is to enable renewables. Anybody who says it isn't doesn't understand. Our job is to keep the lights on. Our job is to keep the wheels turning. And, nothing would make me happier than to be put out of business by something else. But realistically, that isn't going to happen. The energy mix of the United States is still 90% fossil fuels, and probably at least that in most other countries. So, we have a very big challenge ahead of us. And I think each of you needs to decide what part you're going to play. And we will see you Wednesday night, and I will power down this video now.